Hello and welcome to our real-time GPU Raytracing deep dive about Autodesk VRED 21. My name is Simon Nagel and I also welcome my colleague.
Yeah, Danny Tierney. Hi, Simon.
So I think most of you have heard already that Autodesk VRED 2021 is capable of GPU Raytracing. And for showing the performance and quality that GPU Raytracing can offer in VRED 2021, we created a video which is showcasing the functionalities. And we created this video with a customer dataset. We got a Porsche Taycan dataset to create this video. So I would ask you for the favor just to lean back for 1 minute and take a look at this video with us. So first of all, a big thank you to Porsche and especially to Sebastian Rea and Janeta Witoszek, who not only provided the dataset for us, but also gave us a completely VRED file already, which was prepared with materials, with light setups, with certain variations, and with everything that a proper prepared VRED scene needs. And this in combination with the beautiful shape of this car actually made our life a lot easier. So we
Stunning,
made
absolutely. Yeah. I mean, I think the data set itself really well prepared, highly detailed interior. So you can't do much wrong with a data set as beautiful as this. Yeah.
Yeah, so we mainly could just focus on what was important for us, just showing the performance and quality of GPU ray tracing. And it was our task actually to create camera flights, to find viewpoints, to create a storyline about the action that we wanted to show. We wanted to highlight certain features such as design in motion, gap measurement, interior lighting, variations, animations, different light scenarios, interactive lighting review. So that's what we put into that video. Yeah. And also at this point, thank you to CGI Background, who was providing us the background HDR for that video. If you would like to take a second look at this video, I mean, just go to the YouTube link below, or just go to YouTube and search for Porsche Taycan real-time GPU ray tracing with VRED 2021, and you will find that video for review. We were asked after publishing this video by many customers, well, a great video, looks awesome, but what is the hardware spec behind this? Is it real-time? What is it? So to answer this shortly, yes, it is real-time capturing. To give a more detailed answer, we're gonna show the scene live later on to really show you which frame rates do we have for the exterior, for the interior, how much hardware would we actually need, or how much hardware do we need. So all these questions we wanna transparently answer later on during our live session. But before going deeper into GPU ray tracing, I think it is worth to take a look at what GPU ray tracing is about. And it's mainly about improving the visualization quality for virtual prototyping. I think we all know virtual prototyping is about replicating the reality, replicating the real product early in the process to save money and time. And especially in the design area, It's about generating or exploring multiple design options and present those. And working virtually obviously gives you the option to render images, to create images early, to look at scenes interactively, to create movies. So you can virtually communicate and collaborate with your team, and so improve also your workflow early on.
Yeah, and I think just very quickly is we're not trying to do is replace the physical or the clay stage of the design process. Extremely important. The best tools you have really are your hands and your eyes, and you can feel small differences and details while running them across the surface of a clay model. What we're saying is that before you commit to the physical process, that you can try out so much more virtually at a fraction of the cost, and that's the point there.
Absolutely, yeah. And at the same time, it's when you're working virtually, it's quite easy to make changes. So if you detect a quality issue or a design intent issue early in the process, it's a lot easier to change it virtually than doing it in the real world. So, but if you want to make a virtual workflow, if you want to make a virtual decision, you have to have trust in that decision making. You have to have the confidence in this decision making. So you have to be sure that what you see is what you're going to get later on in the process. And for that, we would like to shortly explain what different options are there right now to replicate reality. So first of all, beautiful doesn't necessarily mean real. So if you have a beautiful rendering, a beautiful image of a virtual car, it doesn't necessarily mean that the car will behave exactly like this later on when you build it. So, I mean, for creating design ideas, of course, you want to create your car as beautiful as you can. And definitely go for it, show for it. But you should always be aware of the fact that you need some source of rendering or image generation, which is replicating reality to a certain stage. So in VRED, we can actually see the difference between the two worlds. We have the OpenGL world, which is the world which is generated also by the graphic card, and which is quite similar also to computer games, which is approaching reality, but we are just missing some key features of reality. Whereas on the right side, we see the VRED GPU full GI real-time ray tracing, and obviously we can see that the realism here is a lot higher because we have reflections, we have shadows, we have line bouncing in the scene, we have refractions, so we have all these physical parameters that are also used in the real world, and the software tries to mimic them one by one to generate the same results that we would get in reality. So when you compare those two images, just be aware of the fact that beautiful does not mean real, and that for getting actually a real and correct result, you need to work with the physical properties.
Yeah, and I think the key words here are precision, accuracy, and to be able to reproduce those results consistently as well. So yeah, very clear difference between the two, left and right.
So we are talking about the term ray tracing quite often. So ray tracing is still the best approach to create realistic results in computer graphics. Just to give you a short example, in your real world, we can see with our eyes. And we can see with our eyes because light is coming into our eyes. There's a lot of light in the world, so there's sunlight, there's artificial light, there's light from the sky, and so on. This light is bouncing in the world and is coming into our eyes to tell our brain, well, there's an image. In computer graphics, we have to go the other way around because there's infinite light in the world. Doing something infinity is quite calculation intensive. So for ray tracing, we're doing it the other way around. We just focus on a certain area that we want to see, which is an image. It can be displayed on a screen later on. And this image consists of different pixels. And for each pixel, we are shooting a certain ray into a virtual scene and collect the information about material properties, lights, shadows, and so on. And afterwards, each pixel generates us a result, which is giving us a certain color value. And all these color values together in a picture will generate us an image. So VRED is capable of doing this since, I would say, even 10 years. I think since 2010, VRED has a ray tracing option in there. But until 2020, So until the version 2020, we can see above, it was CPU based. But still, the advantages of ray tracing were there. So it was physically accurate. So early decision making was possible through highly believable visual results. And at the same time, VRED was able to work with physical-based materials and lighting simulations. We could use measured materials, NURBS, and lighting samples. And obviously, if we really want to follow a physical workflow, we have to work with physical parameters, such as photometric parameters for the cameras. We're also able to render spectral colors, because a current color is not just a value. Red is not just red. Red actually is a light wave curve consisting of certain parameters. So we can work with all these parameters to really mimic the physical world in the virtual world. Another big advantage of the ray tracing in VRED is you don't have to prepare your data. So you don't have to reduce your poly count, your node count. You don't have to pre-calculate shadow for it. You basically just drag and drop your files in, apply materials, or automatically apply materials, and you're done. That's basically all you have to do.
Just Simon, very quickly, I think there's the power of having little to no data preparation is sometimes underestimated. For anybody who's prepped a car for a real-time scene, you know how long you can be working on CAD data to get it to run. It could be days, it could be weeks, it could be a team of people working on this. So I think it's quite important to mention that for sure.
Yeah, absolutely. Especially in scenes where you have lots of variations in your scene. So usually you don't have to prepare your data once. You have to prepare it properly for each state: door open, door closed, variant A, variant E, whatsoever. So since you always get a correct calculated image in ray tracing, you don't have to do that. There's also no limitation. I mean, there's no real limitation besides the memory on your computer. So we would say that we are still the most capable solution on the market to handle extensive and complex engineering datasets for high performance visualization and photorealistic quality. So we are just limited by the RAM in our computer. And I have seen datasets running on computers with 4 billion polygons. So it's a lot of data. And it's just running fine because the poly count and the amount of node is not the limit in ray tracing.
Yeah, and I think just in terms of cost, Simon, I mean, when you think about how cheap or affordable RAM has gotten, I think it's rare that you'd find any sort of a desktop workstation with less than 32 gigs of RAM, which is more than enough to handle a large, complex data set. However, let's be clear, there are companies where their use cases are having 20 or 30 cars in a single real-time scene. So that's where maybe a couple of 100 gigs of RAM might be more important. But yeah, the point is still valid.
Yeah, I think, users and customers tend to find use cases that they will have use of all that RAM, which totally makes sense. So, and not to forget, ray tracing is scalable. So if the performance of your ray tracing is too slow for you, you can scale it. So 2 computers are more or less twice as fast as 1 computer. 10 computers are 10 times as fast as 1 computer. And we even tested up to 600 computers, and they are more or less 600 times as fast as 1 computer. They achieved a CPU usage of about 95%. So to be fair, they're not exactly 600 times as fast, but they are 600 times 0.95 times as fast. So we have a linear scaling here, which leads to the conclusion that in this case, hardware can help you to improve your rendering performance. But well, if ray tracing is so great, I mean, what are the challenges? I mean, why are we still working on ray tracing if everything is working fine? And the main issue actually is that a lot of information needs to be calculated. And if a lot of information needs to be calculated, there's a certain demand for quality. So our customers actually want to see this quality. They want to have all this information being calculated to judge the result on this. But having a lot of information calculated also means that we need time to render the results. To get a result, we just have to wait. But I mean, that's exactly the opposite of what our customers want to do. They want to see the results as fast as possible. In an ideal scenario, they want to see it in real time. But to solve this problem, we actually need more hardware. And hardware is spacious and hardware is expensive. So taking a look at the hardware that you need to do the ray tracing process. And let's take a look at the common hardware in a normal user's workstation. So the workstation is below our desk right now. they do have a CPU and they do have a GPU. And the CPU was originally designed to handle a range of tasks quickly, sequentially. One task, next task, next task, and so on. Whereas the GPU was originally generated to render or generate high resolution images and video very quickly. And was designed in a way to do this parallel. So you need most of these devices on your computer. And I'm pretty sure that most of our viewers today have both of those devices on our computer. So unless you're working with an onboard graphic card, but usually you have a GPU in your computer. So let's just take a look at the specs of those pieces of hardware. So the CPU that I have right now has 18 cores. The 18 cores have a certain clock edge, so they have a certain amount of gigahertz. And I have two CPUs in this case on my computer. The GPU on the other side consists of more cores, and we have different cores for different tasks. So we have 4096 CUDA cores, and these CUDA cores in VRED are mainly used to run all the shaders. We also have 72 ray tracing cores, and these ray tracing cores are designed for, in VRED, for creating the or for generating the rays in the scene, for do the actual ray tracing, and for building the acceleration structure, and for calculating the intersection for the triangles. And we also have the tensor cores. I think you might have heard from tensor cores because they are often used for calculating quite rapidly artificial intelligence. And they are used in VRED for generating the denoiser. I just mentioned that in my computer I have 2 CPUs in there. And well, we know that there are workstations where you can put 4 or 8 CPUs in there. But I would say in a common user workstation, you can put 2 CPUs in. In my current workstation, I would be able to fit 3 GPUs. Right now I just have 2, but theoretically I would have space for 3. So I would say in general, a common user workstation can fit 3 GPUs in there. There's a big difference in terms of memory. So the CPU actually is limited by the memory that Windows 10 is providing. And I think Windows 10 Professional for workstations gives you the option to provide 6 terabyte of RAM, whereas we have some limitation on the on the GPU. So we are limited to 48 gigabyte of RAM. Of course, memory sharing is possible, and but it's just not implemented yet in VRED. So one big question is the price. So well, of course, that is not so easy to answer topic. So we have a certain price for the GPU that we pretty much can look up. I mean, the RTX 6000 is about 4,000 euro, whereas a CPU, well, there's so many CPUs on the market, and so we just took a common CPU, in this case with 18 cores, and the price was pretty much the same. It was a little bit below 4,000 euro.
Just a little interjection there. I think the common practice then would be to have, for ray tracing in VRED at least, more cores rather than a higher frequency. So obviously that will increase or influence the price. So that, yeah, that will definitely influence the price. So I think, Simon, altogether, and although you've got two 18 core CPUs, that's 36, and then with hyper-threading, which VRED utilizes for ray tracing, you've got 72, essentially.
Exactly. If I'm counting the 2 CPUs and the threads, the hyper-threading, I have 72 threads in there, absolutely, yes. So, well, if we have a more or less equal price, if we have a more or less equal unit that I can put into my computer, the big question is, what is the speed difference? What is the difference for ray tracing? And we did not exactly know this before we implemented GPU ray tracing in VRED, but we were just looking at the trend. And the trend of CPU development over time was, well, I wouldn't say even, but it was more promising for us to look at GPU performance development. So we expected that the performance gain that we would get from GPU would outpower the performance gain that we had at CPUs. So having these facts in mind, we actually wanted to implement GPU ray tracing in VRED. And we also set up certain goals for that. So we wanted to enable workstation-based ray tracing with good real-time performance. So we wanted our users to achieve interactive frame rates and full GI. We also wanted to provide the ultimate flexibility to our customers, so customers can choose the preferred hardware. And we also want to make sure that it shouldn't really matter for the customers if they're using GPU or CPU. So in the UI, it should look the same. We should have the same feature set for it. We wanted to have the same visual quality. And of course, as our users expect the scalability from CPUs to be linear, we wanted to achieve the same result for the GPU also. We knew from the beginning that there might be some limitations. There are some tasks that cannot be optimized so easy with GPU ray tracing, such as NURBS ray tracing, spectral rendering, and so on. So we were focusing on certain tasks first that we were sure that we could handle them. So we started some time ago. So we did our first tests in 2011. So the guys beyond us with some more experience, we can say, or with some more VRED experience, they might even know this UI. This is VRED 5.5 with the old UI from back then. And we built the first prototype of GPU ray tracing into that version almost 9 years ago. But from the benchmarks that we created, we noticed that the performance gain from GPU was not as high as we expected it to be. And at the same time, we also had certain functions in VRED that were scalable and that we could not replicate to the GPU back then in the way that we wanted it to be. We decided that it's not worth to change to GPU ray tracing 10 years ago.
You probably think that the graphics cards back then, probably the Kepler generation, although great graphics cards for OpenGL. I think the big change is the fact that the new graphics cards have RT cores in them. Although not completely necessary for ray tracing on the GPU, they certainly do help.
Yeah, definitely. I think the change of hardware and especially the RTX cores helped us in our decision making to start GPU ray tracing development in the beginning of 2018. So when we started the development, we wanted to make sure that we could share code between the CPU and between the GPU. So we could use the same interfaces. But at the same time, we knew that CPU ray tracing is recursive. GPU ray tracing is iterative on the other side. So it's a fundamentally different approach of doing the calculation in the ray tracing. It means that in CPU ray tracing, the rays are casted into the scene, they hit a material, and from that on, they get traced more and more and more. Whereas on an iterative approach, you have one loop which is responsible for the ray tracing, for tracing the rays only. So we were aware of the fact that there are different approaches over here. So we focused on path tracing in the first place. We made a first public version of GPU ray tracing in October 2018, and we showed the combination of two GPUs rendering in a VRED scene. And we got quite positive feedback from customers because they actually saw the power and performance that one workstation was capable on. So we kept on working and made the next big presentation at the AIF in April 2019. And we showed the combination of 8 GPUs over here. I think we showed this in combination with a real car. And we also had, I would say real-time frame rates in full global illumination in full HD. After the AIF, there was a change. There was a change on the programming side, because before that we had to open with Optic 6, and afterwards we were able to work with Optic 7, and this helped us a lot because Optic 6 was great to start with. So it was using CUDA as a programming language, and there was a lot of predefined code that we could just use. But we noticed, when we work with many nodes, that's what we usually do, and that's what you as our customers are usually doing. You have a strong limitation for the performance, and also the scaling with multiple GPUs was not too well. So the change to Optic 7 offered us a lot more options. So we were way more flexible for now, and it really helped our expert developers to improve the performance. On the other side, it was a lot of work because we could not use all these predefined programs anymore. we kind of had to write them ourselves, which was, well, good and bad at the same time. It was actually bad because we had to we had to do a lot of work because we kind of had to rewrite all these programs. But it also was good because it gave us a lot more flexibility, and we also could share more code with a CPU ray tracing. At SIGGRAPH last year, we made a first public presentation with 10 GPUs, and I think achieved about, well, real-time results again. We had 25 frames for an exterior scenario. And during that time, we also started our technology preview and beta program with our customers. We were gathering feedback, we were adding features, and we were doing some optimizations before we finally were able to publish GPU ray tracing in April 2020.
Yeah, and just to highlight the point of the technology preview and the beta program, this obviously is critical to increasing the quality, or, well, what our customers want and expect from the software. So a big shout out and thanks to all that participated in the beta program to get the software improved, refined, and essentially released last month. Fantastic work.
So VRED 2021 is released, and well, as already mentioned, we want to provide a maximum flexibility for the hardware choice. So, I mean, it's up to you if you want to use OpenGL, if you want to use GPU or CPU rendering. All you have to do is basically press one icon or one button in the UI to switch between the render modes. VRED GPU ray tracing is available in VRED Pro. You can use 2 GPUs with one VRED Pro license. If you have more GPUs in your computer, you need an additional VRED Core license. So one VRED Core license is capable of licensing one GPU. We're going to talk about different scenarios later on in this presentation. And of course, we just mentioned we recommend RTX cards. But of course, GPU ray tracing is working with Turing, Volta, Pascal, and Maxwell cards as well. But the driver needs to be 4041-6 or newer. There are, well, still some limitations. So photon tracing, for example, does not work yet. That's due to the fact that we wanted to release GPU ray tracing for 2021. So we wanted, or we had to make the call that one of the couple features just were not ready at this point of time. Same goes for cryptomats, fogs, lens flare, some material properties, and also some only partial supported features, such as the quality overrides in the render settings and the pixel filters. There are also some features as spectral rendering and NURBS ray tracing, which are quite challenging to realize on the GPU. So it's not impossible to implement them, but this will be a lot more challenging for us to realize it. So if we want to take a look in the UI how GPU ray tracing is working, let's just take a look at my computer. And as we can see, this is one button, and in this one button we can either say ray tracing off, we can say CPU ray tracing, or we can say GPU ray tracing. And for now, I'm navigating in full HD for now, and you can see the frame rate is about 20 frames. But frame rate is a very relative thing to work with. So right now I'm talking about 20 frames, and as you can see, we can see reflections, we can see self-reflections, we can see refractions and so on. But for those who know VRED, this is only the so-called weighted ray tracing. And weighted tracing is actually not the exact and perfect result for ray tracing. It's just a combination of pre-computed information and reflection in the scene. So, but still, as you can see, with this reflection, with this ray tracing mode, I achieve a very good frame rate. But what you actually want to see is also the result of correct shadows. So if I change to pre-computed plus shadows, I can see interactive shadows in my scene. So if I select parts and if I move parts upwards and downwards, I can see the shadowing of the object, I can see the real-time reflections, so and so far and so on. But what you as customers actually want to see and what you want to base your decisions on is the so-called full global illumination rendering mode. And full global illumination is actually the render mode in VRED, which is mimicking the physical properties as close as possible. So we have reflections, correct shadowing, global illumination, light bouncing in the scene. So all the parameters that we also know from the real world. And as you can see, well, I can work on my workstation. I have 2 RTX cards in my workstation, and I can still work with a frame rate which is acceptable for me to judge my image. And obviously, I can also start my so-called anti-aliasing. And in this case, I kind of leave my real-time mode because I have to wait to generate images. But nevertheless, just after a short amount of seconds, I have a crystal clear image, which is really helping me to base my decisions on.
Yeah, I think that, I mean, that's a beautiful image there, absolutely. And the speed is pretty astounding. But I think not to get too technical into it, it's when you start building in lights on the interior, or you try and simulate the lights for the front and rear lamps, when you've got indirect illumination, color bounces and color bleeding. That's really where you see the difference. And that's where you have to have confidence in the renderer as a physical renderer, so that you're representing reality or mimicking reality on a virtual model.
So this is just showing one computer, and this is just showing the GPU ray tracing. But I think you as viewers, you might be interested in a comparison to a CPU and a comparison to using multiple GPUs together. So we prepared actually some examples on how the GPU is behaving in relation to other parameters. So in this certain scenario, we can see a turntable, a classic turntable on 2 CPUs or on 2 GPUs. I mean, you can read the specs yourself. We are using 2 RTX 8000 cards, or we're using 2 Xenon Gold with 2.6 gigahertz, 12 cores each. And you can obviously see the difference in the frame rate. So in this case, 2 GPUs are just obviously faster than the 2 CPUs on the same computer. We also made a comparison for the Stillframe anti-aliasing, which means that we render out one particular image. And in this case, we're using a slightly different hardware on the CPU. So we have even 2 times 18 cores, so a little bit more. But still, you can see that the 2 GPUs generate 64 samples in full HD in 16 seconds, whereas the 2 CPUs are a bit slower. They finish the image after 102 seconds. Well, now your question might be, well, it's great that CPU and GPU render an image, but does it look the same? So is CPU and GPU rendering the same? Will I get the same result? And the answer is a bit tricky, because it's not really a 100% yes, but it's a very close to 100% yes. Because in this example, we have used 3000 samples. So we used more information per pixel to generate an image. And as I mentioned earlier, we have an iterative approach for GPU ray tracing, where if we have a recursive approach for CPU ray tracing, the way on how the ray tracing is proceed is fundamentally different. So in this scenario, still after 3000 samples, I would just say that a human eye doesn't see any difference. Maybe you can. To be honest, I can't, and I would just say it's impossible, because even if we just make a mathematical comparison between those 2 images, now we can see the images, the difference on the two images. So what we did is we subtracted the value of each pixel from one image to the other. So right now, if we see a black pixel, it means there is no difference. If we see in a non-black pixel, we can say there's a difference. So the brighter
I
the
can only
pixel
see
is,
black here, yeah.
yeah.
Maybe it's my screen, but I literally can't see the difference. But anyway.
Yeah, that's a fair point. I mean, actually, it really depends on your screen. It depends on how you set up your screen. So on my screen, I can see a little bit of a difference. On my second screen, I cannot see a difference. But mainly Danny, you're totally right. You cannot see the difference. So to just enhance this effect and to show you the difference of the screen, we increase the exposure and we increase the contrast of the image. And in this image right now, we can see the exaggerated differences between CPU and GPU ray tracing. But again, the differences in those 2 pictures are this. This is just an exaggeration. So for you, as a rule of thumb, you can keep in mind the more samples you're using, the more likely will the result of your images going to be. So if you're using, let's say, 100,000 samples, you probably will not see any differences in your pictures at all. But again, seeing, I mean, you don't see a difference here. But the more samples you are using, even on a mathematical way, the approach will be more closely. Whereas when working interactively, the difference between CPU and GPU ray tracing will be bigger, just due to the fact that the way on how the rays are traced and distributed in the scenes and how they are calculated is different. So let's take a look on the scalability of GPU ray tracing. So in this example, we are rendering the headlight of the Porsche Macan. We are using a head node in combination with multiple GPUs. We again render 64 samples and we have the denoiser on. And I think you are looking at the numbers already. The 8 GPUs were done after 6 seconds. The 4 GPUs after 11 seconds, the 2 GPUs after 18 seconds, and the 1 GPU will be done after 35 seconds. So obviously in this scenario, 8 GPUs are faster than, less than 8 CPUs.
And I think it's important to note that actually achieving those 64 samples for a complex calculation like this is slightly different than if you're just rendering, for example, a lacquer or just a body component of the, I think you mentioned it was a Macan, I'm going to say Taycan. They're fundamentally different cars. But I think, just the way that you actually reach those samples is dependent on what you're rendering itself and the complexity of that calculation itself.
We also made a benchmark for interactive frame rates. For the interactive frame rates, we are rendering a turntable on a single computer, so we did not use a head node here. We used medium real-time anti-aliasing full HD, and we turned the denoiser on. And the denoiser is actually quite important because the denoiser also is affecting the frame rate here. So you can see that 8 GPUs generate a smooth image, whereas 1 GPU has a certain shuttering effect on the image. So, if we just take a look at the frame rates, we achieved, we achieved 16 frames per second on 8 GPUs and 4 frames per second on 1 GPU. And to be completely honest with you here, we were a bit disappointed about the frame rates because we expected the 8 GPUs to be a lot faster than only 4 times as fast as 1 GPU. So we did the same benchmark again and turned the denoiser off and made the benchmark again. And in this scenario, we noticed that the 8 GPUs were significantly faster. We achieved 20 frames per second, so 25% more than without the denoiser. So if you're working with a denoiser, make sure that the denoiser is working or is calculated on another computer.
Absolutely. And I think that here you can see that the scalability is a lot more than we would have expected without the denoiser working. And there's a couple of best practices that customers have realized. I mean, maybe using a dedicated GV100 card could be better in certain scenarios over using an RTX card, for example, simply because it's in certain cases better at the artificial intelligence denoising. But as Simon mentioned, definitely try and have it on a separate node to eliminate any sort of bottleneck.
And just one final comment about this graphics. This graphic does not mean that 8 GPUs will always give you 20 frames. It just means that in our scenario, with those parameters, with those cars, with this amount of polygons, and so far and so on, in real-time medium anti-aliasing, we achieved 20 frames. We're going to show the Taycan later on in the deep dive on the same 8 GPUs. And there are many scenarios for the exterior where we even achieve 25 to 28 frames. So it really depends on certain parameters, but we will cover this later on in our practical part of the deep dive. We also made a comparison on how fast the performance is if we are using either the native rendering settings in VRED or if we're using the cluster module. In VRED, you have the chance, if you use a workstation with 8 GPUs, for example, if you activate the GPU ray tracing and you have enough licenses on your computer, you will automatically go to GPU ray tracing. But you also have the option to open your cluster module, and in your cluster module to set up a certain cluster. So in this case, you can just use your network settings, type in the IP address of your computer, and just tell him how many GPUs you want to use in your setup, and afterwards start your cluster. So in this scenario, we did compare the GPUs natively in VRED and the 8 GPUs on a localhost cluster. So same hardware, different approach of rendering the image. And we noticed that using the GPUs natively in VRED was actually faster than using those GPUs on an internal cluster.
I think 2 frames is still, for no extra work or cost, just a little bit of experimentation with the cluster setup. It's quite a win.
Yep.
2 frames over 19 frames. I mean, what are we talking about? 10%, 12% increase.
Yeah, and at the same time, we did a comparison. What happens if we have the denoiser? So in this scenario, we have the denoiser running in the left example on the same workstation where we do the rendering. In the right image, we have a workstation, which is running the denoiser, and we're using a cluster computer, which is doing the work. So in the end, the calculation power, so the same RTX cards doing the rendering job, is the same. But the denoiser, since it's on another workstation, the image on the right side is significantly faster than on the left side. So if you're working with a denoiser, again, it's highly recommended to let the denoiser render on another computer if you want to save time and performance. So, if we just take a look at these benchmark results, you can see the link below. It's from our friends from NVIDIA, who also did a benchmark with Autodesk VRED with multiple GPUs compared to a CPU. And, just look at the results yourself. But I think the results that we are just showing here pretty much match to what we have experienced and recorded earlier in our benchmark over here. So, we had certain goals for the GPU ray tracing that we wanted to achieve. Let's just take a look at those if we did. So, we can say yes, we enabled workstation-based ray tracing with good real-time performance on a workstation. The power density is definitely higher than on a CPU. So with the same amounts of units, you can achieve a higher result. But still, we provide the ultimate flexibility to you as customers. I mean, if you want to use a GPU for ray tracing, go for it. I mean, maybe you have a VR computer already with powerful graphic cards, and right now you can do ray tracing on the very same machine. At the other time, if you have a CPU cluster and you're happy with this CPU cluster because you might use it for other use cases as well, it's still perfectly supported, and it will be maintained and I think even still improved in VRED over the future. So it's still one important feature and tool in the VRED software. And either way, no matter what you use, you have the same UI, you have the same settings for both worlds, and you even have a pixel matching if you are using the GPU settings also for your CPU calculation, and if you are using enough samples to render the result. And we also have a linear scaling for multiple GPUs. I think maybe not sure if we can show the usage of the GPUs later on in the benchmark, Danny, but we noticed that we have up to 95% GPU usage on the different computers.
Of course, depending on the content that we're rendering. So obviously in the interior, we get a constant with medium anti-aliasing, probably a constant utilization of anywhere between 90 and 95%, I think. So yeah, for the exterior, you're obviously going to get a little bit less utilized.
So there's just one side story that we experienced during the work with a GPU cluster, and it's about size and transportation. So in our Autodesk Munich office, we have a 48 node CPU cluster, which by now is a bit older. So it's probably 10 to 12 years old. But a couple of years ago, we wanted to transport that cluster from the Gaußenberg office to Munich. And right now we have a similar situation because due to the Corona crisis, we needed to transport the 8 GPU cluster from the Munich office to the home office. And terms of performance, they are more or less equal. I think we've seen the results between GPU and CPU earlier. So I think the performance of both clusters is more or less equal. But the transport was a little bit different. So on the CPU side, since it was a big rack with multiple machines, there was a lot of energy consumption. It was heavy. We needed a special room for it. It wasn't a special room in Gothenburg. It was not easy to ship it from A to B because we couldn't just put it on a pallet like this. So there was a lot of effort actually in coordinating the transport from A to B. And we also needed to make sure that there is space in the Munich office, that the cooling is available, that the power supply is given, and so far and so on. So a lot of people were involved in this process, and I think that's not only at Autodesk. I think that's always if you want to work with this kind of special hardware.
Slight difference, of course, yeah. Getting the similar performing a GPU cluster over to the Munich office. The list is slightly smaller. Basically, it was just put the cluster in the trunk of our car, drive home, carry it upstairs, plug it in, and start the device. So it's night and day for that. So we actually calculated what that cost. It was 50 cents in fuel getting from obviously the Munich office to my home office is a shorter distance than from Gothenburg to the Munich office, but I think it still highlights a nice little anecdote that things are getting smaller and more powerful over the years.
Yeah, and right now the cluster is below your desk, right? I mean, it's right in your room.
Yeah, it's right in my attic here, and I've been, I won't say playing around with it, I've been doing good solid work and research on it for the last 7 weeks that we've been in home. So yeah, a lot of fun. And no, I have not played a single game on it, nor will I.
Perfect. Yeah, we're going to see it in action later on. I'm looking forward to that. VRED Core. I think you have heard VRED Core earlier. So just some short side information about that product. First of all, VRED Core is not a software. It's only a license. So if you want to use it, you have to install either VRED Pro or VRED Render Node. And later on, you can use a license of VRED Core to install it. So don't look for a product which is called VRED Core. Just use VRED Pro or VRED Render Node for it. And licensing VRED Core can be used to license one GPU. I'm going to show some examples in the next slide. The features of VRED Core are, as stated, GPU ray tracing, and it also can be used for GPU ray tracing clustering. In general, it offers the same feature set as VRED Pro, so you can also access the completely open API of VRED Professional. I mean, just imagine it to be a VRED Pro without a UI. It also is available for Windows and for Linux. It is capable of doing streaming, not only on the GPU, but also in OpenGL and for the CPU. And speaking about CPU, you can also use it for CPU clustering. So if you have your CPU cluster, you can also use your VRED Core licenses for your CPU cluster.
Streaming, Simon, I think, not to understate it, it's really, really impressive. And I think it's a game changer. We're not going to address that topic now, but I think on the VRED Pro YouTube channel, there's some videos highlighting the streaming capabilities of VRED onto multiple devices.
Yeah, it's great just to bring VRED content to any browser, to any computer, just by basically accessing one URL that is provided by the VRED web server. So let's just look at some examples. Just imagine you have a single workstation with 3 RTX cards. Because we learned we can put, in most common workstations, 3 RTX cards. So if I have only a VRED Pro license, I can only use 2 of those cards. So I need an additional VRED Core license to run my 3 RTX cards. I could also use 2 VRED Pro licenses for it. Or if I only use this computer for clustering or for streaming, so in cases that I don't need a UI, then VRED Core, 3 VRED Core licenses are also possible. The fine RTX cluster that Dani is using at the very moment with 8 RTX cards can be used by using either 1 VRED Pro and 6 VRED Core, or also 4 VRED Pro licenses, or you use 2 VRED Pro and 4 VRED Core, or you can say, well, I want to use 3 VRED Pro and 2 VRED Core, and so on. If you don't need the UI, then obviously you can also use 8 VRED Core licenses. For the scenario that you use a head node, which has 2 RTX cards, and an RTX server with 8 RTX cards, you need 1 VRED Pro for the head node and 8 VRED cores. Or you need you can use 5 VRED Pros for it, or you use 2 VRED Pros and 6 VRED cores, and so on. If you use this only for clustering, or if you don't need a UI for that, you can use also 10 VRED cores for that. So mentioning this cluster all the time, and coming back to the topic of the Porsche Taycan video in the beginning, we want to show you now the practical part on how GPU ray tracing on a cluster can be used. And yeah, Danny, do you want to talk about the cluster which is in your room right now?
I thought you'd never ask. Never. I don't talk about anything else at the moment. So yeah, just sitting upstairs in my home office here. I've got a head node, so it's just a standard Fujitsu M940 computer with one RTX 8000 GPU in it. So that is doing the denoising. I've got a 10 gigabit connection running from the master into the cluster, in which there are 8 RTX 8000 GPUs. So that would be, I suppose, if we were looking at the scenario from the previous slides, that would be the VRED Pro and the head node, because I need VRED Pro to work and prepare my scene, generally speaking. And then it would be the 8 VRED Core licenses. That would be the variant that we have here. So that's the basic setup.
All right, then I would say let's swap screens. You can share on your side, and let's go into the practical deep dive part of that session.
Absolutely. Thanks very much, Simon. Appreciate it, and look forward to showing you some amazing content on the cluster.
All right, see you in a minute in part number 2.
See you then.